Hello everyone. So let's talk about the traversal algorithm of the binary search tree. So the traversal algorithm of the binary search tree is actually same as the binary tree. So just think about that binary search tree means binary search tree is actually a binary tree. So the way we traverse the way we do the pre-order, in-order or post-order traversal in the binary tree is same as the traversal with the binary search tree. All right. But let's see, look at the algorithm. All right. So here we are doing the pre-order traversal. So we know that pre-order traversal means we first read root, then left, then right. All right. So first we start from the root. First we read the root, then we'll go to the left. But if the left is actually another subtree, that means actually we are going to process the left subtree with the pre-order traversal. We'll complete the subtree with pre-order traversal. All right. So then we are going to go to the right. Now, if right is a another subtree, all right, we are going to continue with our pre-order traversal with the right subtree. All right. So here you can see that the algorithm looks like this. So until the root is not null, all right, we start from the root node. Until the root is not null, we are going to read the root. Okay, we find the data and we read that. Then we go to the left. If left is not null, then we are going to do the same for the left subtree. So you can see that it's a recursive function. So left is not null. So we are going to do the same traversal, means we are going to do the same pre-order traversal with the left subtree. So after we're done with this function, then we are going to check whether right is null or not. If P has a left subtree, then we are going to do the same for the left subtree. I'm sorry. If right is not null, we're going to do the same for the right subtree. So pre-order traversal means root, left, and right. So first read the root, go to the left. If left is a subtree, then do the same traversal for the left subtree. When you are done with left, all right, go to the right of the root. All right, and if right is not null, then you are going to do the same for the right subtree. And that's true for every subtree. All right. So let's see how this will look like when we do the pre-order traversal of this particular tree. All right, so we first read the root 8. Now after that we'll go to the left. So left is a subtree, so it's not null. So we are going to run the same function, means we are going to do the same traversal with the left subtree. So in this subtree, 3 is the root left and 3 is the root. Okay, and we're going to do the same process like root left right. So 3 is the root, so print that, and we'll go first to the left. All right, so that's another subtree, but it has only one child. So after we do the traversal, it will only print 1. Then go to right. So in this right, it will see that root 6, left 4, and right 7. So it will print 6, 4, and 7. All right. So now you are done with actually the whole subtree, right? So you did root, you did left, and now the task of the right. So you'll go to the right. All right. So that's another subtree, and so you are going to do the same root left right for this subtree. Okay. So here you have the root, which is 10. Okay. You go to the left. Left is null, so you will go to the right. So that's another subtree. Okay, so you'll do this subtree with root left right. So you have this root here 14, then left is 13, right is null. So you see that you are done actually this subtree. So we'll return here. You are done with this right subtree, and you are done with actually the whole thing here. So root left right. All right. So that will be our final pre-order traversal. All right. Now the in-order traversal, actually what we do, we read the left first, then root, then right. All All right, and the in-order traversal, after in-order traversal with the binary search tree, you will find actually an interesting result. All right, so here let's look at the algorithm first. If the root is not null, we'll first go to the left. We'll finish the left with in-order traversal. All right, then we'll print the root. Okay, okay, this is our root, so we'll print the root. Then we'll go to the right. All right, and we're going to do the same in-order traversal with the right. So let's do that. So that's our root. We start from here, go to the left. Okay, and left is here, this right child. All right, so in this left, we start from again root. So here also we're going to do left, root, right. Okay, we start from root, and from root we first go to the right. I'm sorry. So from this root we first go to the left. Okay, left, root, right. So finish the left, and that will look like left 1, go to the root 1 3. Then now for this subtree, go to the right. So do the in order with this right child, with this right subtree. So do the in order, it will look like 4 6 7. Okay, so you did left, root, right. Okay, so that means you are done with this left subtree of 8. Okay, now you will go to the root, and you will print root, which is 8. Now you'll go to the right. All right, so for this right subtree, you will do the same left, root, right. All right, and it will look like we don't have any left, so it will print the root first here. All right, 10, it will go to the right, and for this right, this is the right, and it will do the left, root, right. So it will look like 13 and 14. So what we are doing here, and we are doing the in-order traversal in the BST, and the result is actually interesting. So you can see that the result is in the sorted order. Okay. So remember, the thing is that the in-order traversal in the binary search tree will always give you the numbers in the sorted order. Okay, so I mean, you can actually see that what we are doing, we are traversing the node as a left, root, and right. So the left subtree has actually all the node that are less than root, and right subtree has all the node that are greater than root. Okay, and it is same for every subtree. So that's why when we are traversing using left, root, right, all right, in this order, left is always less than root, and root is always less than right. All right, so you will always find the in order traversal in the sorted order. All right, so the post order traversal, the algorithm, you can see we are going to read it like as a left, right, and root. Okay, so let's do the post order traversal here. You can see that first we are starting from the root. So if the left is not null, we are going to do the same post order with left. If the right is not null, we're going to do the same post order with the right. Then we're going to print the root. Okay, so here it will look like, so this is our root. So go to left. Okay, and go to left, and we'll do the post order with this left subtree. Okay, so it will look like, so left, right, root. So I mean, it will look like left 1, right. So here we are going to print 4 7 6, then root 3. All right, then go to right. So here we have right, we don't have left, we don't have any left here. We're going to go to the right. Okay, so here we're going to print 13, no right, root 14. So then root 10, and then finally this root 8. All right, so let's talk about the analysis of the BST operation. Okay, all right, so what type of operation we have talked so far? So the operation we have talked so far in the binary search tree, we can find a node in a binary search tree. We can insert a node in the binary search tree. We can delete a node. All right, and we can do the traversal in the binary search tree. So In the binary search tree, if you remember the way we are finding a node, we are doing the insertion or deletion. Actually, how many operation, how many comparison we are going to need to do that operation, it depends on the height of the tree. Okay, so it doesn't matter that how many node is in the tree. So all the operations, all right, so all the operations, in all of the operations, the number of comparison depends on the height of the tree. Okay, so if this is a binary search tree, so we start from the root, we go either left or right, we go from each of the subtree, we go again from left or right. Okay, so you can see that the number of comparison depends only the height of the tree. Okay, so now what is height of the tree? The height of the tree is a logarithmic. Okay, so if n is the number of node in the tree, all right, and if the tree is a well balanced tree, all right, the height can be as the height can be log of n, all right, and each of the operation in the best case can order of log n, but it can be also as bad as linear. Okay, so so for each of the operation in the binary search tree, all right, so each of the operation in the binary search tree actually has average case order of log n, which is same as the height of the tree. Okay, but in worst case, the operation can be order of n. So let's see an example. Why is that? Because let's see the insertion operation. Okay, let's think about the insertion operation. All right, so if we are trying to insert the node in the binary search tree in the search key order, for example, let's see we have the node comes in a sorted order, say 1 2 3 4 5 6. Okay, so how the insertion of this binary search tree will look like? So let's see we are going to insert every node in a binary search tree in a empty binary search tree. Okay, so that's our first node, so it will be root. So 2 is the second node. Now 2 will be the right child. So 3 will be the right child of 2. 4 will be the right child of 3. Then we're going to add 5, we're going to add 6. Okay, all right. So So if we insert the node in the search key order, that will produce a maximum height binary search tree. So here we have 6 numbers, all right, and here you can see that 6 numbers, and what is the height of this tree? It's 1 2 3 4 5. Okay, if we have n node, the height of the binary search tree, the maximum height can be n minus 1. All right, so in this tree, if we try to find a node in this tree, all right, as the height is actually same as the number of node, all right, so in worst case, the number of comparison for finding or insertion in this binary search tree is same as the number of node, which is the linear time. Okay, but if we insert in a random order, for example, we are trying to insert the nodes, say 3, 6, 4, 5, 2, 1. Okay, it can produce as near minimum height binary search tree. So how this tree will look like? So let's add 3. So 6 will be here. All right, so instead of 4, let's make it 2 and 4 here. Okay, just showing you an example. So 6 will be here the left, I'm sorry, 6 will be here in the right, and then let's add 2. 2 will go in the left. Then add 5. So where will be the 5? So 3, 6, and 5 will be the left of 6. Okay. What about 4? So 4 will go to the right. Okay. So 4 will go to the right of 3 and left of 6, and then left of 5. Okay, and 1. So 1 will go to the 3 2 and 1 here. Okay, so it's actually better than, you can see that the what is the height here, 1 sorry, 1, 2, and 3. Okay, so the height here is 1, 2, 1, 2, and 3. So instead of having height here as same as the number of node, here if we insert the number in a random order, that can produce actually near minimum height binary search tree. Okay, that doesn't guarantee which will create the minimum height binary search tree, but that can produce actually near minimum height binary search tree if we insert the number in just a random order. Okay, so the near minimum height binary search tree is actually logarithmic of the n. All right, so if it's a near minimum height binary search tree, then this will be the best case. All of the operation is going to be order of log 2 base n. But in the worst case, the height can be n minus 1. Okay, what it means that in the worst case, all of the operation can be linear, so order of n. Now, average case, if we consider all of the case, all right, so in the binary search tree, actually average case is close to logarithmic of n plus 1. So we can say that, so the average case operation of the binary search tree operations are order of log n. Okay. So order of operation in binary search tree is retrieval, also average case log n, worst case order of n. If the height is same as the number of node, or number of node minus 1, it can be order of n. So for each other operation, insertion and deletion, the average case can be log n and the worst case can be order of n. Now the traversal, you saw that traversal is actually order of n. Traversal means we're going to traverse all the node in the binary search tree or binary tree. All right. So the traversal are same in the binary search tree and binary tree. All right. So we try to we are traversing all the node. So this is going to be same as the number of node. Okay. So these both are, I mean, in both average case and worst case, that will be order of n operation. All right.